Morning and welcome back to Classical Mechanics 1. This is the 13th meeting, Tuesday, 9th of November, 2021. So we have 28 people present, 29, 30. Okay. So while we wait for the rest of people to join, just remind you that last time we were talking about some examples of forces, particularly the gravitational force, Newton's law of gravitation between point masses, that it is inversely proportional to the square of the distance, and points from one body to the other. It's attractive always, product of the masses. Now, we haven't been very precise with what we mean by mass. So I want to say something about that. Not in great detail, but at least a few essential points about mass. I know this came up earlier, but I wasn't ready to discuss it at that time. Yeah, I'm glad that you have submitted the last assignment on Saturday. We will go over that as well as the previous one, any questions you have. But I don't want to do that right now. I want to continue with the discussion. But are there any questions that I should address? Okay. We are at 43 participants or so. Okay, so then let me share my screen. Yeah. Okay, so if there aren't any questions right now, let us go back to where we were. So I've just given an example of showing that the force that a particle inside a uniform spherical shell feels is zero, and we gave a nice geometric argument as to how the force that different little elements of the shell exert on this mass here are equal and opposite in direction and cancel each other out. And this made essential use of the inverse square nature of the gravitational force proposed by Newton. Now, I want to make a few comments about what we mean by mass. So let me begin by saying that so far we have not been precise about what we mean by the mass of a body or how it is to be fixed. So first, there is the concept of the mass mi of a body that appears in Newton's second law. I'm going to rewrite Newton's second law now as F is equal to mi times A. This m subscript I is called its inertial mass. It's also called its inertia or inertial mass. Previously, we just called it m. Now, we may in fact use Newton's second law itself to give a way of assigning inertial masses to bodies. Okay. We may have various intuitive notions of what mass is, maybe some amount of matter, so on. And that is reasonable to have. But here we are going to use Newton's second law to give an operational definition of how we assign masses to bodies. A very practical approach. So how do we do this? We begin by selecting a reference body. Let's call it A. Yeah, so this could be this bottle or something. Just take some reference body, convenient reference body, and choose units in which its inertial mass is assigned the value 1. Okay, so this is completely arbitrary, but we are free to do that because we are free to choose units. Yeah, so so this unit is not necessarily the kilogram or gram. Yeah, it is some unit. I mean, you can give it some name temporarily. But in any case, we will assign the value 1 to the mass of our reference body. Our reference body is called body A. All right. Then we will apply a force to A. And by force, I mean, for instance, let a compressed spring expand and push it. So we take some reference spring that we have, keep it somewhere and let it expand and push this body. I'm giving a in principle definition, in principle procedure. One can, of course, improve upon this and make it more precise and so on. In any case, we apply a force to A, such as the expansion of a spring. And then we will record the acceleration of A. I mean, at the instant the force acts, the bottle is going to move, and we observe its motion, measure its trajectory, record its trajectory, and compute the rate of change of its velocity. And for simplicity, let's make it move in a straight line or something. Yeah, but that is not important. We're going to measure its instantaneous acceleration when the force is applied. Now we record these things. We record that acceleration. Now, given a body B, whose inertial mass we wish to determine, right? What we will do is apply the very same force to it, namely take the same spring, compress it in the same manner, and let it expand and push that body. So the second body B may be this pencil or this pen, and it's going to be pushed by the same spring. We measure the acceleration of body B, record that. Yeah. So this is all done experimentally. Now we are going to use Newton's second law to assign a mass, inertial mass, to body B. All right. Since the forces applied were the same in Newton's second law, the Fs are the same. Therefore, mass, inertial mass of body B times acceleration of body B must equal inertial mass of body A times acceleration of body A. Yeah. Now, 3 of these have been determined, namely the mass of body A has been assigned the value 1. Accelerations of A and B have been measured, and therefore we can conclude that AB times MB must equal AA times MA. Yeah, of course, these are vectors. Yeah, and since MA has been assigned the value 1, we find that the inertial mass of MB, following from Newton's second law, must be the accelerations of A and B. Okay, so this is our operational procedure for defining the inertial mass of a new body that you wish to assign an inertial mass to. The original body remains as a reference. It is meaningless to talk about the absolute value of its mass. I mean, as far as this discussion is concerned, you do need some reference body or some reference unit in which it has mass 1, or you can choose mass 2 also, doesn't matter. Then that 2 will enter into this formula. So in this manner, we assign inertial masses to various bodies. Of course, this definition of mass is reliant on second law of Newton. There is no going away from that. This is part of the definition. So physical quantities, the values of physical quantities depend on the model or theory in terms of which you are giving those definitions or measurements. So we have to accept that. Okay. So any question about the procedure by which we assign this inertial mass? See, here we are not addressing the question about what is the origin of this mass and so on. Yeah, having given this definition, you are free to study its properties. Like suppose I take a uniform body and cut it into two, will each part have the same inertial mass? This is a relevant question. You can check. And I mean, again, by computing its, I mean, measuring its acceleration and finding out. Yeah, and okay, I mean, we are familiar with some of the properties of this mass that if you divide a body into two, I mean, a uniform mass distribution into two, then both of them have the same masses and so on. Or if you combine two objects, the inertial mass of the composite system is the sum of their masses. Yeah, so this definition of mass does have some nice properties. And so in any case, we are going to work with this definition. I could, of course, have given it as soon as I mentioned Newton's second law, and perhaps I should have done that. But here I have brought it in because we want to compare and contrast it with another notion of mass that is coming up. Okay, so now what is that other notion of mass? Now, on the other hand, the masses that appear in Newton's law of gravity between bodies, yeah, here it's point masses, yeah. So let us look at that. Recall that the force of the second mass on the first mass is given by some constant times m1g times m2g r hat by r squared. Okay. So we have been careful to denote these masses as m1 subscript g and m2 subscript g. These masses are now called the gravitational masses to make a distinction from their inertial masses, which is fixed using Newton's second law. Newton's second law has no reference to gravity. Yeah, so you could use any force you like over there. Yeah, of course, r hat is the unit vector that points from r1 to r2. Yeah, because the force of the second body on the first is directed towards the second body. Yeah, it's attractive. So, but anyway, that is insofar as the direction is concerned. But the point is that certain masses appear in this formula, and we are going to call them gravitational masses. Okay, so now the question arises, and this question was on Newton's mind, and he did address it. Though the matter goes back to Galileo, at least as far as back as Galileo. So, and this is what Galileo was doing. Of course, Galileo didn't have Newton's second law, so this required additional inputs. So let me look at a certain specific context. Let us now focus on the gravitational force of the Earth on small bodies near its surface. Okay, so the small bodies near its surface. I mean, the restriction to small is because there can be inhomogeneities in the gravitational force of the Earth, and we want to avoid some of those things. Yeah, so we are going to look at small objects near the surface of the Earth. Now, at the surface of the Earth, the force on a gravitational mass mg, so I take some body, maybe this bottle, and it has some gravitational mass mg, as yet undetermined. That force is given by Newton's law of gravitation. So minus because it is pointing downwards, yeah, towards the center of the Earth, minus g me mg r hat upon re squared. Here, me is the gravitational mass of the Earth, mg is the gravitational mass of the body of interest, r hat is the unit radially outward pointing vector, and since the force is downward, it is in the direction minus r hat. Yeah. And then you have the square of the distance, in this case, which is roughly the radius of the Earth. Yeah, so this is the force felt by a body near the surface of the Earth. Now we define a new concept called the acceleration due to gravity. Yeah, and well, for that you need Newton's second law. So the acceleration due to gravity of this body is given by A, and that is defined using Newton's second law. It is the ratio of the force that the body feels, in this case the gravitational force it feels, divided by this inertial mass of that body. Okay, so the acceleration due to gravity of this bottle is the acceleration it experiences due to the force of gravity. But in that formula appears the inertial mass of the body because we are using Newton's second law. All right. Now, plugging in the formula for that force, gravitational force, we get this. Yeah. So I'm just making a second use of this gravitational force formula. So you get minus G mass of Earth, gravitational mass of Earth times gravitational mass of body divided by inertial mass of body times, divided by the square of the distance, the square of the radius of the Earth. Okay. So this is, and of course it again points radially inwards. So you have a minus r hat. Okay, so this is the acceleration due to gravity. Yeah, 1 minute. I think we have lost one of the TAs. Perhaps I have to. Pritish, can you make Ankit a co-host? If you cannot, please do tell me, then I will try to do that. Okay, so returning to this discussion, we have given now a formula for the acceleration due to gravity that a body feels. And we notice that this downward pointing acceleration is conventionally denoted small g. And on the face of it, the acceleration due to gravity depends on the body through its inertial and gravitational masses. Okay, both formulae appear here. Both quantities appear here, mg and mi. Both refer to the same body. Okay, so we have now made use of Newton's law of gravitation as well as Newton's second law. Now comes Galileo's observation. So the discussion that follows constitutes what is called the equivalence principle. But let me first begin by stating the experimental observation. Now, the surprising experimental observation, which many of you may be aware of, is that the acceleration due to gravity is the same for all bodies. Okay, we just said that the acceleration due to gravity depends on the gravitational mass as well as inertial mass of the body. But suppose you take this bottle, this mobile phone, this piece of this pen and so on, and drop them from the same height, and ensure that air drag and such things, resistance are minimized, then one finds that all bodies suffer the same acceleration, fall in exactly the same manner, no matter how big, small they are. I mean, provided they are not so big that inhomogeneities in Earth's gravity become important. So this is the surprising experimental observation that all bodies fall in the same manner. More precisely, all bodies undergo the same acceleration due to gravity. And the story of different objects falling in unison, that is in the same manner, from the Leaning Tower of Pisa is a way to remember this. Though it is debatable whether this experiment was actually performed from the Leaning Tower of Pisa in Galileo's time. It was certainly performed later on in Holland, in Delft. But anyway, this is a way to remember it at least. Now, the magnitude of this acceleration, which is common to all bodies, is approximately 9.8 meters per second squared. Okay, so this is something you have seen, I presume. Okay, so now what is the conclusion we can draw from these experiments? Since the acceleration due to gravity depends on the ratio of gravitational to inertial masses, it must then be the case that the ratio mg over mi must be the same for all bodies. Okay. Yeah, it must be a common ratio for all bodies, no matter what their constitution is, shape is, and so on, how much matter they possess, and so on. So now, by absorbing this constant ratio, I mean, this is some number, yeah, we will absorb that into the definition of G. Yeah, suppose you had some previous definition of G, we will rescale it to absorb it into that and arrive at the equality mi equal to mg. Okay, because that ratio was a constant for all bodies. That constant we will absorb into G, capital G, and henceforth we will then conclude that inertial and gravitational masses of all bodies are the same. For any given body, they are the same. Now, this very surprising and interesting result is called the principle of equivalence of inertial and gravitational masses. Okay, so the experimental observation goes back to Galileo's time, but to talk about gravitational and inertial masses required Newton's law of gravitation as well as Newton's Newton's second law. Yeah, so this is really something that came in Newton's time, and Newton observed that, talked about this matter. Now, since we have already assigned inertial masses to bodies, yeah, our operational definition using Newton's second law has already assigned inertial masses to bodies. The equivalence principle then, the equivalence principle then gives us a way of assigning gravitational masses as well. Okay, so through these two experimental procedures, we are able then to assign both gravitational and inertial masses to all bodies relative to some reference body. Yeah. So in some units. So based on all of this, henceforth, we will not make a distinction between inertial and gravitational masses, right? And simply call it the mass of a body.
Excuse me, sir.
Yes, Shubham Kumar, yes.
Yes, sir, I had a doubt. I mean, if we go above that equivalence principle which you wrote,
yes,
sir, so like the mass which is in the formula for the universal law of gravitation, that is like a different property than which is the mass which is used for Newton's second law. Like they are two different properties which we just found out to be like these. Is it that?
Correct. Yeah. Now, at least, and when one formulates the two laws, I mean, there are some constants that appear there. A priori, we do not know what they are. So yes, they are potentially different properties of the two bodies. Yes. Sorry, of a given body. And now we perform experiments in conjunction with these laws. Yeah, I mean, Newton has proposed a certain law. So the entire discussion is within the context of that law. And within the context of that law, and in fact, both of his laws, as well as these observations, we come to the surprising conclusion that these two properties are one and the same. Yes. So that there is some sense in which the gravitational force is entirely some kind of acceleration. Yeah. So yeah, you are right.
Okay, sir. Thank you.
Yeah. Yeah, we will say more about this later on when we talk about accelerated motion. Yeah, but at this point, we are just making a very important observation as to one, how do we assign inertial masses? And second, that the gravitational mass is the same as the inertial mass. So at its core, this is an extremely simple idea, and I have given the summary of it. It does not require any big calculation or anything. Okay.
Just one clarification.
Yes, Romit
this
Roy
point,
Chaudhary, yes.
yes. At this point, the only justification for the gravitational law is the inverse square law, right? So we're saying that gravity propagates inversely with the square of distance. So that's why it depends on some random properties, which we're defining as gravitational mass.
Yeah. Okay. So I mean, I don't know what you mean by random properties, but yes, propagate and all. I'm a bit careful about using these words. I mean, Newton has proposed a certain force between two masses, two objects. Yes. And that force is much weaker when the masses are farther and farther apart. And through various studies of planetary motion and so on, he comes to the conclusion that perhaps it falls off as the inverse square of distance. These are all deductions from observations, yes. And that it does depend, I mean, the bigger the body, somehow that force is larger. This too is an experimental observation. And based on that, that bigness of the body is encapsulated in something that we will call its gravitational mass. Yes, if that is what you are asking, yes.
But if we don't have a way to a priori define what, if we don't have a way to a priori define what this mass is without referring to inertial mass, how did we come to the conclusion that gravitational force is the product of these two gravitational masses?
Okay, the short answer is it's a proposal. Yeah, we can check a proposal and throw it out if it does not produce results in accordance with observation. So it is as simple as that. We don't need any definition. It is simply a parameter in the law. Newton is proposing a procedure to study the force between bodies. That is all. I mean, anybody can propose any procedure involving any number of parameters. Then we check, does it have any use for us? It is as simple as that. We do not need any further definition. You need not even have called this thing a mass. You could have called it the color of the two bodies. Yeah, or you don't like word color, let us call it some other name, yedai. Okay, I mean, Tamil, yedai is weight or something. So you can call these two the yedais of the bodies. Yeah. Now, there are some property. We are not saying what that property is. We are giving a procedure to measure that property using various other laws and procedures. Romit, yes. Now I have somehow lost the connection.
That's helpful. Thank you.
Is that okay?
Yes, sir, that's okay.
All right. Yeah. 1 second. I am not able to. Okay. Okay, so now the screen sharing is back. Okay, any other question? Yeah, all right. Now, in this context, I want to talk about a couple of other terms which often come up in this connection. And one of them is called the weight. So let us give some kind of definition for the weight. Yeah. So the weight of a body, and we have in mind bodies near the Earth. The weight of a body is defined as the Earth's gravitational force acting on it. Okay. And this is going to be our definition, our working definition. So at the surface of the Earth, the weight of a body of mass m, and here mass, I mean, it's the gravitational mass or inertial mass, they're both the same. Yeah, but originally what appeared there was the gravitational mass. The weight of the body of mass m is denoted capital W, boldface. It's a vector. It points radially inward and has a magnitude equal to g times mass of the Earth times mass of body divided by square of radius of the Earth. Okay, so we will combine all these constants like g, capital M, and Re squared yeah, and put them inside this boldface small g, which we had defined previously. It is the acceleration due to gravity. Yeah. So we notice then that the weight of a body is simply m times g, and points vertically downwards. Yeah. So the weight is a force, and in particular, it is measured in newtons in SI units. Okay. So that is what we mean by the weight of a body. Notice that the weight of a body defined above is independent of the motion of the body. Yeah, the force is independent of the motion of the body. So this is what we will define as the weight of the body. Yeah. Now there is another concept that is related to the weight that is sometimes confused with it. So I just want to say something about that. This concept of a normal reaction. So consider a body of mass m at rest on the floor, yeah, on the earth. Now balance of forces in the vertical direction, I mean, it's at rest relative to the earth. So balance of forces in the vertical direction implies that the floor must exert a normal reaction force n upwards, which must equal m times g in magnitude. So this is what is called the normal reaction. This is the force that the floor exerts to support the body. Here the body was at rest, and you have this balance of forces. Okay. Now, just to help us think about these things in a slightly different context, let us suppose that the body is not at rest on the earth, but is in an elevator that accelerates upwards at the rate a. Okay, so you're going up the building at some, and the elevator is accelerating upwards at the rate a. Now, inside that elevator, we have this body. So the force due to gravity on that mass, that body, is still its weight. Okay, that has not changed. The weight doesn't change with the motion of the body. So that is still mg. W is mg. Now we can apply Newton's second law to this situation, the body in the elevator, and write down mass times acceleration. So this acceleration is upwards, is equal to the sum of forces acting on the body. So the forces acting on the body are, one is the normal reaction force due to the floor of the elevator, and then there's the weight of the body. So combining these two, taking W equal to mg to the other side, we find that the N force is equal to m times a minus g. Okay. Let us just get our wits right about this. Now the normal reaction force points upwards. Yeah, N is pointing upwards. The weight is pointing downwards. Acceleration is also pointing upwards. Okay, so this is the setup. So A points upwards, G points downwards. So as a consequence, the magnitude of the normal reaction is m times A plus G. Okay, because G is actually pointing downwards. So it becomes A plus G when you look at the magnitude. So the normal reaction that this body feels in an upward accelerating elevator is a little bit more than m times g. That is when it was at rest. It is more by an amount equal to m times a, where a is the acceleration, upward acceleration of the elevator. Now this is the force, this N is the force that the floor of the elevator must exert upwards to support the body. Okay, if it doesn't exert that force, the body will break the floor. Now we have just observed that the magnitude of N exceeds the magnitude of the weight of the body, exceeds it by an amount equal to m times a. Now what we usually call a weighing scale, it is usually calibrated in such a way to read the number magnitude of n upon g. Okay, so weighing machines are set up in order to display the value of this normal reaction force divided by g. The normal reaction force is how much force that weighing machine has to press upwards in order to support the body. Okay, so that is what it displays, of course, divided by g. And so that is so. In other words, in an elevator, the weighing scale will read a larger number than when the elevator is at rest. Elevator going upwards, I meant. Yeah. The opposite holds for the elevator going downwards. Okay, so I mean, so anyway, this is a simple use of the ideas of normal reaction and weight and Newton's second law. So I hope this is clear. Okay. I mean, the important thing is to have our definitions clear. Otherwise, we get a bit confused. By definitions here, I mean the definition of normal reaction or the definition of the weight and so on. Okay. So this is what I wanted to say about the gravitational force and these few comments about mass and inertial and gravitational mass and the equivalence principle. But there are other forces also that we should be aware of. One second, I have somebody at the door. Please give me a moment. Yeah, so as I was saying, there are other forces of interest as well. Principal among those is the electrostatic force, electric force. Now, charged particles exert electrostatic forces on each other. Yeah, charged particles at rest. And they can, unlike gravity, they can attract as well as repel. And the force between point charges is summarized in Coulomb's law, which is very similar to Newton's law of gravitation between point masses. So I'm sure you have all met this somewhere or the other. So Coulomb's law says that the electrostatic force between charges is proportional to the product of electric charges and falls off inversely with the square of the distance, okay? Distance of separation. And as I pointed out, unlike gravity, which is always attractive, the electric force can be repulsive as well as attractive, depending on the nature of the charges. And if it is attractive, we will say that the two charges are of like sign. And if it is, if it is repulsive, we will say they are of like sign. And if it's attractive, they are of opposite signs. And in this manner, we would assign the signs to the charges of various bodies. And having done that, we will conclude that charges of the same sign repel and unlike charges attract. Okay. So the point is that this force is very similar to gravitational, at least the formula. This electric force is very important because many of the forces we are familiar with have their microscopic origin in the electrostatic forces between molecules. For instance, the frictional force between a body and a surface, the frictional force between a body and the surface, or the viscous force between layers of a fluid, or between a fluid and a body moving through it, are all macroscopic manifestations of electric forces. So many of the forces we experience in our daily lives, other than gravity, have their origin in electric forces. It really rules our life in many, many ways. The force that a stretched string exerts also has its microscopic origin in electric forces between molecules. Okay, so a lot of the forces we experience do have their origin in electric forces. For this reason, the electric force is called a fundamental force though that word is somewhat overused, but it has become common to call the electric force a fundamental force, whereas friction and viscosity are called emergent or phenomenological forces. Okay. I will say in a moment what I mean by that. In a sense, they emerge from considering many electric forces and their effects among the constituents of the system. I mean, there's another way to classify these forces as well. Friction and viscosity are also examples of contact forces. They arise when they are exerted when bodies are in contact. Okay? Whereas the gravitational force between bodies is present even when they are far separated. Whereas friction is when they are in contact. I mean, this is a different property. Now, though these forces like friction and viscosity and the force in a string or in a rubber band arise from electrostatic interactions between molecules, it is often not practical to deduce their strength and nature from microscopic considerations. This is by and large hopeless. While it is all nice to say that friction arises from electricity, to derive the value of that friction from studying electric forces between molecules is very, very difficult. Yeah. So rather than do that in practice, macroscopic forces like, these effective emergent forces like friction are usually modeled or described via effective macroscopic formulae. Yeah. I mean, we don't go back to Coulomb's law to tell how tell the value of the friction that a ball is going to experience on the surface it moves on. Yeah, rather we use some kind of effective macroscopic formulae based on experimental measurements, and one of those is Hooke's law for a spring. I mean, even the force that a spring exerts when it is compressed and expands also has its origin in microscopic electric forces between molecules, but it is hopeless to try to get that by studying individual molecules. Yeah, so instead we study a spring and see what kind of force it exerts and encode that in some kind of effective law. In this case, it's called Hooke's law. We'll talk more about Hooke's law. Yeah. So examples of such effective laws at large distances are the following. One or two I'll mention. So you have the drag force on a sphere moving slowly through a fluid. Okay, so you have the fluid in this room or in a bucket of water, and if you have a ball falling through that, there is the drag force, viscous drag. By experimentation, one finds that this viscous drag is approximately proportional to the speed, that is, bodies traveling faster experience more viscous drag, and provided they go relatively slow. Yeah. And that it points in a direction opposite to the velocity of the moving body. Okay. So, yeah, so that is one way in which one might encode or summarize what the drag force is. Yeah, by doing experiments with falling spheres in a jar of liquid. Similarly, neighboring segments of a stretched string. So you have a string here, and you have I've enlarged it a bit. You have neighboring segments of the stretched string. Yeah, they are found to exert a tensional force on each other. So suppose the string is stretched between two clamps here, then the element here pulls the element here to the left, and the element here pulls the element in the middle. So I've got A, B, C. I've got three pieces of string. Because the string itself is stretched, C exerts a rightward force on B, and A exerts a leftward force on B, and this force is called tension. Yeah, it tends to stretch the string. Yeah, so so as I was saying, neighboring segments of a stretched string are found to exert a tensional force on each other, tending to elongate each segment. Now again, you may want to know what this tension is, so you have to measure it somehow, not go back to electricity to find it. Yeah, and the tension can usually be modeled as a constant force along the length of the stretched string. So this is a reasonable model. Its value, of course, will depend on how you have clamped them and what force you have applied over there. Yeah, which one can measure and find. Yeah, so these are called emergent or phenomenological forces, unlike gravity. So let me make a statement about that. So aside from gravity and electromagnetic forces, which we will designate as fundamental forces, there are two more fundamental forces, namely the weak and strong nuclear forces, which we are not familiar with in everyday life, except in some exceptional situations. So the strong and weak nuclear forces are very short-ranged. They typically act over nuclear and subnuclear distances. And they are responsible for phenomena that we do see if you look carefully, such as radioactive decay and for binding neutrons and protons in nuclei. Okay, so the weak and strong nuclear forces are responsible respectively for radioactive decay like beta decay and for the binding of neutrons and protons in nuclei. Okay, so I'm just mentioning that there are these four fundamental forces. This is not the matter that we are going to discuss in this course, but it is good to know. Any discussion about this? Any question about this general discussion about forces?
So in principle, you can derive the coefficient of friction using the Coulomb's constant and atomic numbers of the material, right?
Yes, in principle, not just, yeah, you need the nature of the material, how it is constituted. Maybe it has some kind of crystal structure.
Oh,
you
okay,
will
sir.
need all that information. Yeah,
Okay, sir. Okay.
because different materials will, yeah, I mean, a ribbon may have a different kind of force compared to a rubber band and so on. Yeah, so it depends on the material. But yeah, it comes down finally to the electric forces between molecules. Indeed.
Okay.
In principle, it's possible. Yeah, and people do such things. Yeah, I mean, but you need, it is not analytically possible to handle such things, but one does large-scale numerical modeling of molecular dynamical simulations, and it is possible in principle to calculate this. It is not at all straightforward, and for most purposes, we will not try to do that at all because it is pointless. It is much better to measure it and see what the consequences of those macroscopic laws are. Occasionally, we do want to derive them from microscopic principles, and yes, that is a worthy enterprise in some contexts. Yeah, to calculate the viscosity of water at certain temperature, I mean, it's an interesting question. If you want to get it from microscopic principles, one could try to do it. Okay, that was Milan Paul. Okay, any other question? Yeah, if not, now I want to return to some of the principles of and quantities we study in mechanics. So this completes our discussion of Newton's laws of motion, as well as Galileo's principle of relativity, and some examples of forces. And we have also, in the process, I hope, clarified what we mean by mass. It may not be what you expected, but we have to be very practical. We have to have operational definition of what mass is. It's a whole other thing to think what mass may be and so on. But insofar as Newton's laws are concerned, this is how we will define masses. Okay, so now we come back to somewhat less qualitative matters. Oh, by the way, we also talked about the equivalence principle, which is a very, very important principle of physics, and at the heart of the study of gravity, and was exploited very well by Einstein. Okay, but now let us come back to some topics which might be called analytical dynamics, analytical mechanics. So let us start with things we are familiar with. I want to talk a little bit about momentum, energy, work, angular momentum, and what we mean by dynamical variables. Okay, so let us introduce all these concepts. Yeah, Yeah, so as you are aware, the momentum, or sometimes called the linear momentum, usually we don't use the word linear, drop it. The linear momentum of a particle of mass m moving at velocity v, yeah, in some inertial frame, is defined as p equal to mv. Okay, in some frame, it's simply the product of the mass with the velocity. Now, if there is no force, that is, if it's a free particle, then each of the components of this momentum, linear momentum, is conserved. Yeah, and that is a consequence of Newton's second law, which says that the rate of change of momentum is equal to the force, but if there is no force, then p dot is 0, and p is equal to px, py, pz. So each of these components must be independent of time. Okay. Yeah, and if, of course, there may be a force, but suppose the force acts only downwards, then you still have the, so if it acts only downwards, then pz dot will be equal to the force, px dot and py dot will still be 0. Okay, so then the horizontal components of momentum would still be conserved. When we say conserved, we mean they don't change with time. I'll be much more precise about that, but I'm introducing this idea through examples right now. Okay, so this is linear momentum. Next, we come to the concept of work. Work done by a force, which will help us also to introduce the concept of a conservative force. Okay, so here we are going to make use of our earlier study of vector calculus, vectors and line integrals and so on. So let us remind ourselves what the work done by a force is. We were a bit cavalier about this earlier. Let us be a bit more precise. So suppose a particle of mass m, yeah, actually the mass doesn't matter so much here. Suppose a particle is moved from a position A to a position B along a trajectory. We'll call the trajectory gamma. It is some curve. Yeah. And that trajectory, along that trajectory, the position vector of the particle r of t varies, of course, with time. And the time that is elapsed lies between t0 and t1. Okay, so this is what we will suppose. Yeah, so the picture should make it clear. A particle moves from a point A to a point B along a certain trajectory under the influence of a certain force. Now, the force definitely need not point tangent to the curve that the particle follows. As you are aware, even for circular motion, the force points inwards, whereas the particle may move tangentially. Okay, so force points in some direction. Now, we can define the concept of the work done by the force during this process, and it is given by the line integral W of gamma. So gamma was our trajectory, W is the work. So this is the work done by the force F, W of gamma. So that is the line integral F dot dr over the curve gamma. So at each point along the curve, we find the force dot product with the dr, the infinitesimal displacement vector, and integrate. Okay. I can write this more explicitly as an integral over time, which is the parameter along the curve. So we write it as f dot dr dt times dt. Okay. Now dr dt is, of course, the velocity of the body. Yeah, and then instead of integrating over the curve, we will now integrate over time in interval t0 to t1. Okay, so now the integral is over an interval of the real line t0 to t1. So this is the work done. Notice that the force itself may depend on location. Yeah, it's not necessarily a constant. May depend on the location r and may change with time. Okay, so the force, that is why we need to perform an integral. Otherwise, you could take the f outside. Now, according to the definition and the picture, in general, this work that the force F does depends on the trajectory. Okay, I mean, we have to perform this integral. It depends on the trajectory and not just on the endpoints, namely r of t0 equal to a and r of t1 equal to b. Okay, so in general, the work depends on the path of the particle traversed by the particle, its trajectory. However, so any question about this work? See, F dot dr is the infinitesimal work done by the force F when the particle is displaced dr. Okay? And we are simply adding up all these infinitesimal works that are done. Okay, that is what the integral does for us.
Sir, question.
Yes. Yes, Ruptak Majumdar.
Sir,
Yes.
like, yes, sir. Sir, it's like if we take another like a trajectory which is similar to this trajectory itself, but it goes through the path faster. I mean, like.
Wait a minute. Given an initial location, final location, a trajectory is a solution of Newton's equation of motion. So either it goes at this speed or it doesn't go at all. There is only one way to go. Yeah, so it is not an option for us. I mean, Newton's laws specify the trajectory given initial conditions. Okay, here the situation a bit different. I'm talking about some initial location, final location, and so on. Yeah, but this is a trajectory. So it's not possible to traverse a trajectory at a different speed. Then it will not solve the same equation. Is that understandable?
Yes, sir. Yes, sir.
Okay. All right. So is there any more to your question, right?
Sir, like I had asked this question because it's like if like it travels, I mean, like the time is
what you have in mind is a different trajectory. It won't look like this at all. It is some other trajectory. See, the concept of the work done by a force along a trajectory is well defined. The trajectory is specified by Newton's solution of Newton's equations of motion. The force is given to you. You simply have to calculate this quantity. There is no option. If you change the trajectory, then the amount of force work will be different in general. My sense is that you are thinking, what if the particle traverses this same curve at a different speed than the one it is doing currently? Now that, that different speed motion is not a motion at all. It is some concocted idea in our heads. It is not a solution of equation of motion. If this was a solution of equation of motion.
Yes, sir.
The limits will change. Yeah. If it's T0 and T1 will change, right? If it's traveling at a different velocity.
Yeah. I mean, I don't know what he had in mind. Maybe he thought it will go faster here and slower there and somehow make up the time. But the point is that if you're changing the speed, I mean, the Newton's law itself will start getting violated, right? I mean, the acceleration may change and it will not be equal to the force divided by the mass. So you cannot change r of t and hope to recover the same solution. Solve the same equation.
Yes, sir. Like I had in mind that it's like will the work be conserved if it goes faster or slower? I mean, like by the definition of work.
No, I think that is not a meaningful question at this stage. We can ask a different question about. See, to talk about conservation of something, your thoughts are interesting. So far, we can talk about the conservation of something if it is something that depends, say, on time. Yeah, something that depends on time. We can ask: does it depend on time or does it not depend on time? So we talked about momentum of a particle. That is that's a quantity which could change with time. Now, in certain circumstances, it doesn't change. So then it's conserved. Now, the work here is not a function of time. It is a function of an entire trajectory. It's the function of initial time, final time, and so on. What does it even mean to say, is W conserved? Yeah, we will have to give a meaning to that statement in the first place.
Yes, sir.
Okay, good. Yeah, anyway, it is good to think about such things. It is a legitimate question. Maybe there is another trajectory that doesn't look like this one, but goes in some other route between the same 2 points, yeah, in the same duration of time, yeah, that can happen. And one can legitimately ask the question, along that other trajectory, is the work done the same or not? Yeah, okay. And the answer to that question has to be found out. We don't have the answer right away. So to calculate the work done in that new trajectory, yeah, so suppose the force field was such that it's possible to go from here to there in another route also, okay, along a different trajectory, we can legitimately ask whether the work done along this trajectory is the same as the work done by the force along this trajectory. That is a legitimate question. And but we don't have an answer to that. That depends on the details.
Yes, sir. Yes.
Okay. Yeah. Okay. Very good. Yeah. I mean, there are very explicit examples of this. Right. I mean, you have the sun and you have the earth here. Suppose you're setting the earth off in motion, and you are somehow aware that it follows some kind of elliptical orbit around the sun. I mean, initially you have a option. Am I going to start counterclockwise or clockwise? I mean, initial conditions are going to determine that. You will get, you will end up at the other end. Suppose you start at one end, you will end up at perigee. You can end up at apogee. The trajectories would be different, and you can ask whether the gravitational force does the same work in both routes or not. Yeah, and there may be symmetries that ensure that it does the same work. They may not also. Yeah, so.
Yes,
Okay.
sir.
Okay, good. Yeah, so now we have defined what we mean by the work done by a force along a trajectory. It is not some any old curve. You are free to consider any old curve, but then I will not call it the work done along a trajectory. And that concept is also interesting and useful. It's just that we are not talking about it here. Okay, now we come to a further observation. That is, however, there are a special class of forces. So I just observed that the work done by a force along a trajectory depends on the whole trajectory, generally speaking, not just on the endpoints. Okay. We can ask, are there forces for which the work done by the force depends only on the endpoints? Yeah, no matter what the endpoints may be, as long as there's a trajectory joining them, does the work depend only on the endpoints? In fact, it is possible. There is a special class of forces where this work depends only on the endpoints. And these are the forces we wish to define right now. So in fact, suppose the force field, I mean, recall the force is a vector field. Suppose the force field is given by, I mean, for conventional purposes, the negative gradient of a potential function. That is, going back to our vector calculus notation, f of r, which is a vector field, suppose it is the negative gradient of a scalar function, v of r. Okay, so given a function v of r, you take its gradient. Let me remind you what the gradient is. So if you have a function v of x, y, z, then the gradient of v is now a vector field whose components are given by the partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z. Okay, and all of this depends on the location at which you took the derivative. Okay, so this is a vector field. And for convenience, we put a minus sign here. Yeah, that has some convenience. Yeah, I will talk about that later. But suppose the force field was the negative gradient of some potential function. Then let us, first we will give such forces a name. We will call them conservative forces. For reasons, the reason for the name will become clear in a moment, the next section. Suppose that is the case, then let us compute the work and see what happens. Yeah. So the work done by this conservative force, yeah, let us see what it is. So we have to evaluate this integral. In place of the force, I substitute minus grad v, minus gradient of v, dotted with dr dt dt. Okay, so this is the integral we wish to perform. Now I claim that using the chain rule of differentiation, this combination, namely grad v dotted with dr dt, is actually the time derivative of the function v evaluated at the location r of t. Okay, so I think I should explain that in a moment. Yeah, let us do that. So here I wrote the formula for grad v. Okay, this is grad v. Similarly, we have dr dt. Okay, so let me suppose that that is given then by dx dt, comma dy dt, comma dz dt. Okay, so r is equal to x, y, z. All of these are functions of time. That is what tells you what the trajectory is. Okay, at each point along the trajectory, the position vector r has the components x of t, comma y of t, and z of t. Now we are told to take the dot product of these two things. So when I take the dot product, let me write down what I get. Grad v dotted with dr dt. Okay, so comparing with what we have, dot product will multiply the first component with the first, second with the second, and third with third. So let me write that here. It's going to be partial v partial x dx dt plus partial v partial y dy dt plus partial v partial z dz dt. Okay, so this is the dot product. Now, using the chain rule, I am going to declare that this is simply d by dt of v of x of t, y of t, z of t. Okay, this is a sort of three-dimensional version of the chain rule. You have a function of three variables, each of which depends on time, and you want to differentiate with respect to time. Well, you must do what the chain rule tells you, namely first differentiate v with respect to the first argument, namely x. That is what partial v partial x is, and then differentiate the argument, namely x, with respect to time. Add to that the similarly dy dt times partial v partial y, and finally partial v partial z times dz dt. Okay, so this is a three-dimensional version of the chain rule, extended from one variable calculus to multi-variable calculus. I hope this calculation at least is clear to you. So if I then insert this over here, the work done becomes minus the integral with respect to time of dv dt. Okay. Any question about how we reached this point? This is a nice use of the chain rule of differentiation. Okay, then we are nearly done, because now we are integrating with respect to time. Now we are down to one variable calculus. Okay, we are down to one variable calculus. We are differentiating some function with respect to time and then integrating it. And therefore, by the fundamental theorem of calculus, or what you are already familiar with, this is given by the antiderivative evaluated at the two limits. So it would be v evaluated at the upper limit of integration minus v evaluated at the lower limit of integration. And there was a minus sign already, so the two get reversed. So we get v of r of t1 minus v of r of t0, okay, with a minus sign overall. And remember, we called r of t1 as b and r of t0 as a. So that's how we get this formula. Okay, so lo and behold, the work done by this conservative force only depends on the potential function at the two endpoints of the trajectory. All the dependence on the intermediate locations has gone away. Okay, so the work done in this case may be physically interpreted as the drop in the potential. I mean, the potential started as V of A, it ended up as V of B. The difference I call the drop, and we are saying that the work done is the drop in the potential for a conservative force field. So please take a moment to absorb this calculation and its conclusion. Any question about it? or the use of the gradient notation and the dot product. Please become comfortable with it. Okay. If there aren't any questions about that, let me emphasize again the conclusion that in general, the work done by a force field depends on the process, depends on the trajectory followed by the particle. However, there are a special class of forces called conservative forces, where the force is the negative gradient of a potential function. For such forces, the work done only depends on the endpoints of the trajectory. Okay, so this is a remarkable feature of conservative forces. Now you ask, why is it called conservative force? It's because a conservative force leads to a certain conservation law, namely the conservation of a certain energy. So far, we have not discussed energy. This is the first time, except sort of colloquially. Yeah. So let me introduce this concept of energy. Now, first of all, the fact of the matter is that many interesting forces, such as the gravitational force, the electrostatic force, the simple harmonic restoring force of a spring, etc. Yeah, but not all. Yeah, there are many forces which are not of this sort. Friction being a prime example, or viscous forces, they are not of this sort. So many interesting forces are conservative. Namely, it is possible to find a potential function V such that the force field can be expressed as a gradient. Okay, so now we restrict ourselves to such forces for the current discussion. Now, for such conservative forces, Newton's second law, let us see what it says. Let us rewrite it. For such conservative forces, Newton's second law implies that the sum of kinetic and potential energies, defined here as half m r dot squared. Yeah, so what is this? Half m x dot squared plus y dot squared plus z dot squared. Okay, so that's what I mean by this. Half m square of the velocity, it's a dot product of velocity with itself, plus the potential function evaluated at the location r. Yeah. Yeah. So this E function, which I have defined, in general depends on time. Okay. Because x, y, and z all depend on time. R depends on time. So it is half m r dot dotted with r dot. Yeah, this dot product plus V of r of t. Okay. So all of these things depend on time. So in general, E should be some function of time. Okay. But let us compute its time derivative and see what we get. Well, it turns out that this energy is conserved along trajectories. So we're going to make use of the equation of motion of Newton to show this. So let's compute E dot, the rate of change of this energy. Yeah, we have to differentiate both the terms. So the first one, we are going to use the product rule of differentiation. You have a product of two functions of time, or you can go down to the component form, x dot squared plus y dot squared plus z dot squared. So when you differentiate with respect to time, this expression, for example, you will get half m times 2x dot times x double dot. Yeah, plus 2y dot times y double dot plus 2z dot times z double dot. Okay. I can summarize that whole thing by canceling this 2 and write it as m, so m remains, times r dot dotted with r double dot. Yeah, r dot is x dot y dot z dot, and r double dot is x double dot y double dot z double dot. So if I take the dot product of these two vectors, I will get the expression on the right hand side. So here is our rate of change of kinetic energy. I add to that the rate of change of potential energy. Now there again, we have to use the chain rule of differentiation, because V is a function of R, which is a function of time. The chain rule says to differentiate V with respect to time, first differentiate it with respect to R, and then differentiate R with respect to time. Okay. So as we did before, I encourage you to check this. The derivative of v with respect to r is actually the gradient, because you can differentiate with respect to x or y or z. And having done each of those, you must then differentiate x with respect to time and y with respect to time and z with respect to time, and add those all up. The result is this dot product. I mean, it's identical to the work to the formula we used earlier in calculating the work. Yeah, so we will have here grad v, gradient of v dotted with r dot. Now something very interesting happens. Yeah, we have a common factor in both these terms, namely r dot. So we'll take that out. So this formula, I'll write it as r dot times mr double dot plus gradient of v. Okay, but the quantity now in parentheses is identically 0 by the quantity in parentheses is identically 0 by Newton's equation of motion. Yeah, because Newton's equation of motion for a conservative force says that mr double dot is equal to the force, which is minus gradient of the potential function. Yeah, so putting that here, taking this to the left hand side, mr double dot plus grad v is 0, and therefore E dot is 0. Okay, so we have proved that the energy doesn't change along a trajectory. Okay, if you compute the energy along any old curve, it will change along the curve. Yeah, you need two very important assumptions in arriving at this result. The force needs to be conservative, and you need to proceed along a trajectory. Otherwise, this conclusion becomes suspect. Okay, so yeah, so Apratim Ghosh said got disconnected because of energy, sorry, electricity outage. Yeah, yeah, we are having some heavy rain here in Chennai. Okay, so that is the conservation of energy. I think we are out of time. So there's more to be said on this, but perhaps I will do that next time on Thursday. Any questions at this stage about conservative force or how we showed it leads to conserved energy? Conserved means doesn't change along the trajectory, independent of time, along the trajectory. Yeah, any questions at this stage?
I had a question.
I'm not able to hear if somebody is asking.
Sorry, sir, just a second.
Okay, Gautam Vishwanathan, could you speak up if you are asking? Okay.
Yes, sir. Sorry, there were some mic issues.
Yes.
I think I missed something. I didn't quite catch exactly where we used the assumption that like we're working with a trajectory when we showed that.
What is a trajectory, first of all? A trajectory is a curve that satisfies Newton's equation of motion.
Right.
So here in deriving this conclusion, we have definitely made use of Newton's equation of motion. In computing E dot, yeah, we see R of t defines a curve. Yeah. But is that curve a solution of the equation of motion or not? If it is, we will designate it as a trajectory. All right. So in that sense, we have definitely made use of the equation of motion to assign the value 0 to this quantity in parentheses. So does that make clear how we have used it?
Yeah, and so because we've used that equation of motion, it doesn't apply. It doesn't necessarily apply if it's not a trajectory, and so. Okay.
Absolutely, yeah. Along simply some curve whose parameter you call t, there is no guarantee that r double dot will be equal to the force by the mass. Yeah, there is no such guarantee.
Right, that makes sense, sir. Thank you.
Okay, yes. There is some other question. So the total energy E is defined as the sum of kinetic and potential energy. Yes, indeed. Ankit Gayan has asked. Yes, indeed. Yes, we do define the total energy for a conservative force field to be the sum of these two expressions, kinetic and potential energies. Yeah. And the reason for that definition is that that quantity is conserved for a conservative force. That's why it's a good definition. You could define anything else you like, but this one is nice. Any other question? Okay, Ankit says all right. Yeah, any other question?
Yeah.
Yes, please.
For conservative field, I understood that the potential energy is defined as the scalar field whose gradient gives a force, right?
Correct.
So,
With a minus
but
sign,
how?
with a small minus sign. Yeah.
Yeah, with minus sorry. But what about why is the kinetic energy defined in that way? Like half mv squared?
Okay. Yeah. So here I simply proposed a formula, computed derivative, found it to be 0. Yeah. So I have not motivated this formula. Indeed, a good question. So next time I will, I mean, in the next point is to somehow deduce this formula simply starting from Newton's equation. Yeah. So your question is a very good one. We will next time start with Newton's equation, do some manipulation with it, and somehow arrive at this formula for energy. And I hope then when we do that, you will see why this half mv squared is coming.
Because of the work energy theorem. Yeah.
Yeah, it is also related to the work energy theorem, which relates the work done to the change in kinetic energy. That's true. Or one can think in terms of integrating factors and so on. So yeah, we will discuss these viewpoints.
Okay, sir. Thank you, sir.
Sure. I think the most straightforward viewpoint is to simply take Newton's law and see how the conserved energy emerges from that. And I do intend to do that next time. So your question, I hope, will be addressed. Okay. Any other question?
Sir, can I ask a question? It is very relevant to the topic now.
Yes.
Can I simply ask it? Yes, sir.
Yes.
Sir, so if you're pumping water from a pipe, okay, from a hose, then you feel a backward force, right?
Okay.
From where do you feel that?
Pumping water from a hose.
Yes.
Okay.
How do you feel that also? So if you're firing a gun, like a bullet is inside the gun and you are holding the gun, but when we are pumping water, the water is coming from some kind of water tank, but we are not holding the water tank, right?
Yeah, but I mean, the force that the water tank or the pump, see, the pump may be far away, but the fluid being a medium that is able to transmit forces, yeah, it's able to transmit the pressure. The pressure applied by that motor far away is transmitted through that fluid, through the pipe and the hose pipe and so on. So in many ways, it is simply a gun whose barrel is very, very long and convoluted and turns and so on. So I think as matter of physics principle is concerned, the pressure in the fluid is distributed or is transmitted over a long distance and so on. But it's not very, I mean, it's almost like you have extended the barrel of the gun so that it became far away. I mean, the motor was far away. It is very similar in that sense. If I understand your question.
Sir, right. But we are holding the barrel, right? I mean, the gun, the whole gun is in our hand. Kind of
yes.
Thing. But here, we are just holding the end of the hose, right?
Okay.
And still we are feeling a backward force.
Okay. Maybe I need to
no,
re-understand your question or the puzzle. Okay. So you are saying, or you're asserting that when I hold I connect a pipe to a tap and pour water from it, I feel a backward force, is it?
Yes, sir.
Have you tried this out?
Yes.
Okay, fine. All right. Let me, if I'm able to give some further suggestion about how one might think about this, I will try to do so. If I mean, what I said, if it is not adequate.
Okay, sir.
Yeah,
thank you.
Yeah.
Okay, thank you.
Sure. Yeah. I mean, my initial instinct is that the pressure in the water is transmitted all the way from the motor up to the point where you are holding the pipe.
Yes, I'll think about that too, sir.
Okay. All right. Any other question right now? Yeah, Romit Roy Chaudhary has some comment about it as well. Yeah, I mean, perhaps let's say the water source is vertical and the hose is fired horizontally. In that case, the hose must exert a directed net force to direct the flow of the water, which acts as the force of the fluid, I think. Okay, I would need to read this more carefully to understand. Yeah, I would think of breaking up the problem into several segments of the pipe, and each segment of the pipe exerts some force. and the original one came from the motor, but if you break up the pipe into several, for convenience at least, it may look somewhat similar to your gun problem. At present, this is all I'm able to suggest. Okay, any other question? If not, we shall meet on Thursday morning at 11:50 as usual, and I wish you a good afternoon then. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.